So the first presenter is Ingo Stahlkopf. Ingo studied at the University of Applied Science in Berlin, and after completing his diploma thesis at Airbus Industries in Hamburg, he started his career at BAE Batteries, excuse me, a traditional industrial battery manufacturer as product manager. In 2014, he entered the world of infrared temperature measurement as sales manager at Optris, also a Berlin-based manufacturer of non-contact temperature measurement devices, such as pyrometers and infrared cameras. Since 2018, he has been the head of sales at Optris GmbH. Ingo, please. Forgot to say the title. So the correct temperature measurement during tempering process of different types of coated glass.
Thank you. Yeah, hello, welcome to my presentation. Yeah, thank you for the introduction. As mentioned, yeah, I'm going to talk about secrets about temperature measurement on glass, which is not that easy, as we hopefully will see. Let me spend a few words before we start with the introduction of the company of Optris to one don't know us already. The Optris is based in Berlin. What we are doing, we are a producer of infrared measurement devices such as pyrometers, infrared cameras, including accessories, and the software plays a big role, of course. It all happens in Berlin. We are 115 employees right now. And yeah, the headquarters and the production is based in Berlin. That's what we're very proud of. And that means, of course, we calibrate our units. We want to have accurate devices. We assemble them, we solder them, put them together, etc. So yeah, that happens all in Berlin, where our company is based. Of course, we are also active worldwide. We have our worldwide global distribution network. So you will find anywhere of the world somebody who knows about the Optris products. Yeah, basically today we're talking about glass, especially for glass tempering. But actually, yeah, what we are doing is temperature measurement, and that of course happens in different industries. So just to get an overview, we are active in metal, we are active in the plastic industry, in electronics, safety issues, even in the food sector, very important application, as you can see. We are active pharmacy, and last not least also in the world of glass. The temperature plays a big role. So we can say finally, yeah, temperature is one of the most wanted value to measure. Somebody says it's the second most important value to measure right after the time. So that's why we are almost everywhere active. So also in the glass industry. Yeah, and the world of glass itself, again, is more or less special in some different areas. So we have container glass, we have float glass, we have glass tempering, we have quality issues. So yeah, many things. But today, that's the topic. We want to talk about glass temperatures, especially for the tempering process. And yeah, I think you know about this application, probably more than me. So that's actually what it's about. It's about sheet glass tempering. We talk about line scanners because we want to see, or we want to interact to have a certain furniture temperature measurement to know what's going on. Yeah, that's actually what it's about. Here we are. So why are we doing that? Why is the temperature so important during the tempering process? I mean, to the expert of you, it's clear. We want to know about the heat distribution on the glass surface. We need to have a homogeneous thermal distribution, which gives us a feedback about the furnace condition in the end. So the operator can control and create a high quality glass. But also on the other hand, it's a very important part of the documentation to document the quality control, to assure that the recipe was fulfilled completely according to the demanded values. And yeah, in the end, it's about the heat management, the settings of the furnace to consider to keep the right conditions to have a high quality glass in the end. So, what is the state of the art so far? I mean, the idea of measuring glass right during the tempering process is not new. We are talking about line scanners, or we have line scanners, the state of the art, product to get the temperatures of the glass surface. It's a technology, probably approximately 20 years old. And how is it working? Here we see, actually those line scanners are looking with a single point parameter to a rotating mirror to create line by line temperature informations. And those temperature informations we can put to each other to create an infrared image or temperature matrix. We put some colors on it and then you see the bed of the glass you have. So that's actually the main idea of this line scanner, but there are some advantages and disadvantages on that. And the first thing, of course, it's easy. We just have to handle one single spot parameter, which means we have one point only to measure, which is moved across the line. On the other hand, we have a moving part in it, and we need a certain distance because it's based on the technique, a fixed focus unit. And that means across the whole line, we have varying spot size. So in the center of the glass, we have a smaller spot size, and if we move it from one to the other, the size of my spot is varying slightly. In the end, that means a little deviations in temperature reading because the temperature of what the sensor sees is the average of each area in here. And if you move it from one side to the other, then it is slightly varying. So that's one of the main, that's the functionality, let's say. There are some other topics to mention. Here we see such a typical line scanner so far. It is quite heavy, quite bulky. It's a quite big unit. And typically it's installed above the line. Here we see one sample looking downwards to the top of the glass. And to adjust those scanners can mean a little effort. And some other things are to be considered. There is a quite large optics opening in here, you see, which is a potential hazard for dust and dirt to get or to harm the measurement. And that's why it can be a bit critical. Of course, there's a solution for it. You can install an air pressure on it to clean the optics permanently, to keep it clean. But that, of course, means also to bring some media, like in this case, air in it, and if wanted you can even actively cool it with water, which means another higher effort. So that's the state of the art. I'm sure you have seen some similar installations like this, that's the state. And of course that means some effort. Those sensors, or in general when we talk about temperature measurement, they operate at specific wavelengths. And here I just want to remind to some basics of these infrared measurement. The problem is the glass is sometimes behave a little special on behalf of radiation. That makes it a bit difficult for us to measure the temperature if we don't do it the right way. When we talk about infrared cameras, everybody thinks about these handheld devices, or even you have seen in the do-it-yourself market those portable infrared units, and most of them are operating at wavelengths between 8 and 14 microns. But I just don't want to start with the whole basics of infrared, but just to name it, that's the classical, let's call it classical wavelengths of infrared. But in the world of glass, we are using different wavelengths. We are using some filters or specific sensors operating at specific wavelengths. If you see in the data sheets, no matter from which manufacturer, you will see the glass units always will operate at 5 or 7.9 microns. And the reason for that is to be seen in that chart over here. Here we see a graphic of 3 more or less common glass types, and you see we see the distribution over the different wavelengths, the emissivity according to the wavelengths. And we see clearly there are some ranges with a rather low emissivity, but there are also two points with rather high emissivity, which means, in other words, the counterpart of transparency. So that means here we have a lower reflection. And if we take only this narrow gap or this narrow gap, we have a good chance to get the true temperature value by reading with the sensor. Here I have mentioned 2 examples. Both are showing the same glass. The left picture is looking downwards to a float glass, measured with a standard infrared imager operating between 8 and 14 microns. And we see here in the graph, 8 to 40 means the whole range. It's covered by this camera. And of course, there is some area with low emissivity or lower emissivity, and that has an influence on our measurement. And we see it if we look to this image, compare with this image, which is measuring only at 7.9 microns. You see here some reflections visible, which in the end is some reflections from the rooftop. There are colder beams, which of course has an influence of my measurement. On the right side, we see we limit the external radiation because we don't see this part with lower emissivity. We only look at this optical window, and that gives us a much more precise value. So that's the basic, that's clear. That's why those line scanners or pyrometers operating for glass or designed for glass are operating at this wavelengths. So we could say, okay, all fine, we can measure glass at this wavelengths, but the world is not that easy as often. When it comes to coatings and when it comes to reduction of emissivity by additional coatings, then we have a problem. So here we see a true case. We want to temper, you want to temper glass, typically, or very often, especially for architectural issues, glass with a certain coating. The coating is designed to reflect the sunlight, typically, which means it is by purpose a reduced emissivity. That's why we have those low E glass. The problem is, if we want to measure the temperature, this is what our sensor is seeing. We're looking from the top, right after the tempering process, and we see the temperature. I'm sorry, this is moved somehow, but the temperature is indicated with 135 degrees C. In fact, it has a temperature of 577 in this case. So this is actually what the camera is measuring. Even we have done it with a certain proper temperature device operating at 7.9 microns. Here we see the truth. How could we do this? Of course, even what the sensor is looking, we can calculate something. We can reduce the emissivity settings in the unit. We can reference it with a pyrometer from underneath. So we can calculate this temperature if we want, just on the software side. Yeah? But is this the truth? Is this what we really want to see? It is close to it, yeah. And if we compare, this is the same image, just with the right emissivity settings. Still, if we are honest, we see there's some strange behavior in the image, and it comes even worse. Here's one image, the same situation. We measured from the top. We reference these values with a single point pyrometer looking from underneath where there's no coating. So we have the true temperature on one point. That means we can calculate the true image out of it, but it is only half of the truth. If there is some former disturbance like a rooftop heater like this on this side, even by calculating this true range of temperature, you can still have these problems. And in this case, you see there are some stripes, and this is everything but not the truth of the temperature. Yeah? So that's why low E glass to measure from the top is very difficult. And it comes even worse. If we measured such types of glass with the grinded edge, to make it suitable for special coatings, putting in the frame, you need to get rid of the coating at the edge, as you know. We can reference this image again from underneath, but here now the problem is, inside we have a coating with a very low emissivity. We have to calculate it back to the truth, but at the edges here we have a grinded area with a very high emissivity. So it is a lot of effort. In the end, we can create a nice image, and if everything is fine, we can even arrange it to a nice temperature profile. But to repeat this, and especially for different types of glass, it's a very high effort. It's very complicated to do it online on the machine, and so it creates some problem. So to make it short, it is possible to measure from the top, but if you want to see the truth regarding temperatures of coated glass, then it is definitely not the reliable way. But the good news is the coating is normally only on the top side, right? So the question is, why not measuring completely from below? Looking to the side where there's no coating, where there is a rather high emissivity, where there's stable conditions. And yeah, obviously it seems to be easy. We have stable conditions, we have much less disturbances, we have less reflections, and we have always the same distance. If you have different thicknesses, you don't even have to refocus the device. The problem is, on the other side, of course, there are tough conditions. We are limited in space. We have broken glass, for instance. And yeah, the device itself, normally the standard device, what we have seen, they are quite bulky. It's hard to handle them. You need to connect them, and then you have to assure them to be stable. So that's why we thought about this, and I think we found a good solution to get an approach to make this happen. So we just, we thought there must be another way compared to measuring with one single point sensor, only one point. As we have infrared imagers, what about to use our small cameras to put it under the glass and create the complete image out of it? The problem is the limited height. If we want to see the whole width of the glass, we have to use two cameras. And luckily, we were able to put together both infrared images into one to have one signal of the glass or of the camera to see the whole glass. And furthermore, when you start to think about using infrared cameras in that way, there are plenty of benefits compared to these typical line scanners. Because it is an imager, that means we can handle the whole infrared image. We can go into the software and we can do a lot of things just digitally. All you need is to place the cameras underneath the glass. You have to arrange it. Sounds a little easier than it is, I know, but once it is done, the rest can be done only on the software side. You see here, this colleague is just setting up the image, put the position of the line we want to scan, because we have just a narrow gap to measure it. But in the end, this is what we want to read out. We want to see a nice line scan. We want to see the heat distribution. And yeah, then of course, we want to have some more benefits like temperature on single areas. We want to have a history, what we have done before. We want to have a live view, so we can really see what's going on, is cars coming or not. So we can handle this infrared image completely, which makes it much more flexible compared to the other solution. So that's the actual message. If we want to get rid of the coating, we just should avoid to measure it. Just looking from below, that is a stable situation, and that gives us good, precise temperature values which we can handle. So there are some other benefits regarding dimensions. We are handling two cameras, which means we have, or we can organize the shapes as we want. If there's a larger range, you know, there are some big furnaces available with the width of more than 4 meters. In this case, we could even turn the image to take the diagonal out of it to create our long line scan. Or we just put it next to each other to have a nice view and to have a nice image. Yeah. So that's the bottom-up measurement, the principle. We can use it. Yeah, there are some more fine adjustments. That is one video just to have an idea how it should look. Here we see the whole scan line, and we can put it next to each other. You can digitally position it, and then the question is also how to position it, and there are some features in the software. We can even have an automatic line adjustment just to find automatically where the hottest spot. So some benefits, but I don't want to bother you with some more details. If you have those questions about the software, the settings, the options, just let me know. Our booth is just around the corner over here. Then we can talk about more details. So yeah, that's actually it so far. And I hope you liked it.